Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. I hope you got a chance to go through the lecture which I had on the simplex method and you quite understood the process. In that lecture, I have also discussed how to solve the problem when you cannot find the basic feasible solution, particularly when the constraint is greater or equal to, or you'll see one more constraint in today's lecture when it is equal to. So in that process, we had used the simplex method in two different phases and solved the problem. So overall, whenever we are using the simplex method, it is very clear that our intention is to identify the non-basic variable which is going to create the maximum change. So for that, we look into that del fq, the unit change of the non-basic variable, and select it to replace one of the current basic variable which is going to reach the zero value sooner. For that, we are looking into the ratio, and whichever the ratio is least, we are choosing that for the replacement. So this process continued until we reach to a point when we cannot find any non-basic variable that can replace a current basic variable. Once we reach there, we stop and report the current base variable and its corresponding value as the optimum solution. With this understanding, as I had said in the last class, that apart from the two-phase method, there are other methods to solve. In today's lecture, we'll be discussing about one such method, and we'll also discuss about a few special cases. We'll start the class by revisiting the standard format of the LPP. So in the standard format, as we know, we are going to maximize a linear function which is indicated here for the constraints, which could be equality as well as inequality constraint, and where each of the design variable or decision variables are expected to be 0 or more. Whenever we are looking into the standard format, and if we are looking into the equality constraint, the equality constraint can be represented as a pair of inequality constraint, which is represented here, which is less or equal to the constant, and as well as greater and equal to the constant. So these two pairs of inequality constraint can bring the value to the equality constraint, which will satisfy this particular equation. Now, if we want to use this set of inequality constraint to replace the equality constraint, we would require more number of slack variables. So instead of doing that, we could as well introduce the artificial variable to deal with the equality constraint. Once we introduce the artificial variable, the process is same as we had discussed in our last class. So in this particular example, we have one equality constraint which is shown here, and once we rewrite these constraints, we can indicate or we can introduce the artificial variable a1 in that particular constraint and represent the constraints as shown here. With this revised formulation, we can represent the tableau with the help of the two phase. In the first phase, for the artificial variable, we are going to indicate the coefficient as -1 and use that as one of the basic variable, and try to solve the tableau considering all the other variable coefficient as 0. Once we solve this particular set of tableau, we can see that in the first iteration, the non-basic variable x1 is going to bring in the maximum change in the objective function. So we are going to bring that non-basic variable into the system by finding out the basic variable which is going to reach 0 sooner. In this case the ratio represents that, and S1 has that list value. So we are going to replace S1 with X1 and get the revised tableau, which is shown here. In the revised tableau, when we find out the non-basic variable which is going to bring the maximum change in the objective function, we see that x2 is that variable, and when we check with the current basic variable, we find that a1 is the variable which is going to reach 0 sooner, so we need to replace a1 with x2. Once we replace this, we get the revised tableau which looks like this, and at this point, once we calculate the del fq for all the non-basic variables, we see that either those values are 0 or negative. So there is no other non-basic variable which we can use to replace a basic variable. So at this point the first phase ends and we obtain the basic feasible solution and the tableau to carry it forward for the second phase. When we go to the second phase, we introduce the corresponding coefficients and we drop the artificial variable from the tableau, keeping all other variables and the tableau cell information as is. Then when we estimate the maximum change in the objective function, we find that S1 variable, which is now a non-basic variable, is going to bring the maximum change. Hence we would be selecting it and find out the basic variable which it is going to replace. In that process we find out that it is going to replace S2. Once we revise the tableau after replacement, we find that the del fq for all the non-basic variable are either 0 or negative value, and hence we are not going to process any further. So in this case we see that the only non-basic variable which we have is S2 and the value is negative 3/2. So at this point we are going to stop or terminate the process and report the objective function value as 36 and the optimum solution x1 as 2, x2 as 6, and this is our optimum solution. Now, as I had said earlier, and as you have seen in this case, we require two phases to solve the LPP problem whenever we have an artificial variable. There is an alternative method to that, where we can actually solve the problem using a single phase. One such method is Big M method. In the Big M method, what we do is, instead of considering the negative one for the artificial variable and all the other variable coefficient as 0, we set up the problem by keeping the coefficient as is for all the design variable and set the artificial variable to a very large negative number. This large negative number, we assume it to be so large that whatever the coefficient, each of the other variable has no effect or almost negligible effect on the objective function value. So with that understanding, let us see how we can introduce the Big M method in the simplex solution process through this example. So in this example, we have one of the constraint which is an equality constraint, and once we transform the constraint and rewrite after introducing the slack variable and artificial variable, we obtain this. This problem, when we represent it in a tableau, we can write the tableau by having all the variables including the artificial variable and the coefficients, the respective coefficients which we are indicating here, but the artificial variable has a coefficient negative m. M is a very big number. We choose the basic variable representing the slack variable and the artificial variable. So this becomes our first tableau, and then we represent all the cells of the tableau, and once we do that, we find out the non-basic variable which is going to bring in maximum change to the objective function. So for that reason we calculated the del fq, and once we calculated the del fq, we get the non-basic variable x1 value as this and x2 value as this. In this case, we see that x1 has a quantity 3 times m, whereas x2 has a quantity 2 times m. Since m is a very big number, and with respect to this big number, all the other coefficient has a minimal effect or negligible effect on the objective function value, then we can clearly see that 3m, or rather we say 3 plus 3m, is substantially bigger than the 5 plus 2m. Hence, we are choosing x1 as the entering variable, and then we find out the current basic variable which is going to live. For that reason, we are finding the ratio, and from the ratio it is clear that S1 has the least ratio, so S1 is going to reach the 0 value sooner, and hence we are going to replace S1 with X1. Once we do that, the revised tableau is going to look like this, and in this case now we have a new basic variable x1 and its corresponding coefficient is indicated here. Then in this tableau we adjust all the cells accordingly as required. After doing that, we estimate the del fq, and when we do that, we find the non-basic variable x2 has the highest del fq value. So we are going to bring in x2 in the basic variable. For that, we need to find out current basic variable which is going to live, and when we do the ratio, we find that a1 has the least ratio, so a1 is going to live, and if a1 is leaving, then we can rewrite our tableau as shown here. Now we have x1 and x2 as the base variable or basic variable, corresponding coefficients are there, and then we find out the cells of the basic tableau by adjusting, so that we have 1 for the basic variable and all the other values are 0 by doing the row operations. And at this point, once we estimate the del fq, we find that S1, a non-basic variable, has the highest value. Now when we estimate it for A1, we see that the value is 5 by 2 minus m, and m being a very big number, eventually this is going to be less than 0, which means this is negative number and this is positive. So we are going to bring in S1 into the system, and we need to find out the current basic variable which is going to replace. For that purpose, again, once we do the ratio, we find out that S2 is going to be replaced. So once we do this swap, we obtain the tableau as shown here. At this point, once we estimate the del fq for all the non-basic variable, in this case the both non-basic variable have a negative value, so we cannot replace any of the current basic variable with the available non-basic variable. It means our final answer, the x1 variable is going to be 2, x2 is going to be 6, and the overall objective function is going to be 36. So you see that in this particular problem, when we solved, we did not go from phase 1 to phase 2. By using a very high negative or very large negative coefficient for a1 artificial variable, we could solve this problem in a single phase. So this method is quite useful in solving any problem wherever we need to introduce the artificial variable. You can in fact try the BGAM method on the problem which I had discussed in the previous class. Now we'll look into some of the special cases. For example, as I said, in the standard format of the linear programming problem which we are using here in this class, we are using the objective function as a linear function which we are maximizing. The constraint, it could be equality constraint, and if it is a inequality constraint, it should be less or equal to a constant value. So in this case, if we obtain this constant value as negative value, then what should we do? So that is the case here which we are showing it. In this case, we can easily convert or rewrite this particular constraint into this form. We have a greater equal to sign, and we have already shown you how to convert this greater equal to into a standard format and then solve the problem. Whenever you have a problem where the right hand side of the inequality constraint is negative, you know how to transfer it into a standard format. Another concern could be about the each individual variable. We said each individual variable are supposed to be greater equal to 0. What if we need the variable which can take a negative constant value? In that case, we can introduce a dummy variable which we are calling it as xj dash, which is equal to xj minus lj. Here xj we said greater equal to lj, so let me write this. We can write it as xj minus lj greater equal to 0. If we introduce the dummy variable as xj dash to replace this, then definitely xj dash is greater equal to 0, and this is what we need it in our standard problem. So what we do is, wherever we have xj, we replace it with this particular term, so which means we are going to write xj equal to xj dash plus lj, and lj is a negative number. Let us look into an example. In this particular problem, we have one of the constant which has to be greater than negative 10. So lj in this case is equal to negative 10. Our xj dash is going to be xj minus 10. And if we replace xj by this equation, we can see that the objective function is going to be this one. So negative 10 times 3, negative 30, which is coming here. In the second constraint, which is less equal to 4, so x1 is equal to, in this case, x1 dash minus 10 less equal to 4, so x1 dash less equal to 14. Same way, there is no x1 in this case, so it remains as is. Here again, once we replace, the 18 becomes 48, and we have this problem. We can use the simplex method to solve this problem as usual, and once we solve, we'll get the value of x1 dash, and if we come back and replace it, we can get the actual x1 value. This is how we are going to convert in case if we need a particular design variable to adopt certain value which is negative. We may also have a situation when there is no bound to a particular design variable or decision variable. So it can take negative value as well as positive value. In that case, we can actually introduce two dummy variables. These are indicated as xj dash and xj double dash, and both of these are going to be greater or equal to 0. If we introduce this, we can easily represent our current variable xj by this equation and replace it in the overall objective function and the constraints to modify the problem and use it. So in this case, again, let us see, this is the similar problem where we say x1 has no bound, so only x2 is supposed to be greater or equal to 0. So x1 we are replacing with x1 dash and x1 double dash. So we are writing the objective function as shown here. The constraint, the first constraint as this, second constraint no change, the third constraint as this, and then we say x1 dash, x1 double dash and x2 all are greater or equal to 0. And this now we can solve using the simplex method we have discussed so far. There are other special cases as well. For example, if we want to minimize, so far we said our standard problem is maximization. So what if we need to minimize an objective function? In that case, we can either transform the objective function to a maximization problem by multiplying with -1. Or if you recall, we said that whenever we are choosing a non-basic variable, we should choose the maximum positive value and replace that non-basic variable with the current basic variable that reaches the 0 value sooner or which has the ratio the least. So while choosing the non-basic variable, instead of choosing the maximum positive value, we can actually choose the maximum non-positive value, that is the most negative del fq. If we choose that, then we are going to minimize the function. So only with this change in the simplex method we can manage the minimization problem. So one way is to convert the minimization problem to a maximization problem by multiplying the objective function with -1. The other way is to choose the maximum non-positive value for the non-basic variable while using the simplex method and follow the process to minimize the given objective function. In certain cases, we may also encounter a problem which may not have a feasible solution. As we had said that if we are unable to find out a feasible solution, we are not very sure how to start with the feasible solution. In that case, we introduce the two-phase method or the big M method. So if the original problem has no feasible solution, basically when we introduce the big M method or phase 1 method, we'll find out that the final solution which we are going to obtain will have at least one artificial variable greater than 0. So if an artificial variable has greater than 0 value, that means it is going to stay in the tableau and not going to allow the method to conclude. So at that point, we know that we have a problem which has no feasible solution. If you recall, in one of the examples, we said that there are two variables and both variables had equal largest del fq value. If we have that situation, we chose one randomly. So in case of those situations, to tie break and find out the entering basic variable, we arbitrarily choose one of the non-basic variable from this and move forward. The same thing applies for the leaving basic variable. Again, if we find two basic variable have similar or same ratio, we do choose one of them randomly and move forward. The other case could be we may have a problem with no living basic variable. So this is a case of unbound objective function. If you have formed a tableau and we are trying to solve, we are unable to find any basic variable which is going to live, then basically we cannot solve that problem, as this problem is an unbound problem. Then another condition could be a problem which has multiple optimal solutions. In this case, we'll find that the tableau is repeating itself over the process. And if we see so, then we can clearly say that we have reached to a solution which has multiple optimal solution. So let us look into some of the basic example. Here is one of the example, or rather there are two examples for which you will find no feasible solution. If you try to solve these two problems, you will find that the artificial variable introduced will never converge to 0. As I had indicated in the previous slide, that if the artificial variable never converges to 0, we cannot get a solution, and we can say at this point that it has no feasible solution. Here is another example for an unbound objective function. In this case, if you try to solve the problem, you will find that we'll reach a point where there is no living basic variable. And if we reach to that point, again we know that the objective function is unbound, and hence we cannot get the solution. So these are the situations which you are going to encounter while using the simplex method. I would encourage you to use the simplex method, solve these problems, and see your result, how you are concluding based on what we have discussed. Here is an example. This is for the multiple optimal solution. If you try to optimize this particular problem, you will see that it has multiple optimal solution, and once you form the tableau based on this problem, you will see this tableau, the first tableau, will lead to this tableau where x1 is entering and s1 is leaving. So in this tableau we get x1 as the basic variable, and once we compute the del fq, we find now x2 is going to enter and s3 is going to leave. So after this, when we revise the tableau, we'll get this particular tableau where we have x1, x2, and we still retain one of the slack variable s2. At this point, when we estimate the del fq, we see that the s1 slack variable has a value 0, and this is the point where we generally stop, because once we say the termination criteria is like del fq is less equal to 0, so we have reached there, we generally stop. However, a non-basic variable yielding del fq equal to 0, which is in this case, indicates that any increase of that variable would not influence the maximum objective function value. So if a tableau is extended after finding a non-basic variable yielding del fq equal to 0, in all other cases you will notice that no change in the decision variable values happen. However, in this example, if we try to go to the next step, we'll see that there is a change in the values of the basic decision variable x1 and x2. Now it is 2 and 6. Earlier it was 4 and 3, and we come to a point which is again saying that s2 can enter based on the similar principle, and if we do that, it will yield the tableau which is shown here. So between these two, it's going to keep on moving. So this repeating tableau indicates that the given problem had multiple solutions. So like the way I have shown you here in this case, you can try to solve the other problems for the unbound objective function or no feasible solutions, and see on your own how the tableau is behaving and what solution you are obtaining. So in today's lecture, we saw how to deal with the equality constraint, and also we learned a new method, big M method, which can be used to solve linear programming problems wherever there is a requirement of an artificial variable. So the big M method is an advancement of the two-phase method, where we do not require to solve the problem into two different phases. Rather, we can use the same simplex method in a single phase by considering the artificial variable with a very large coefficient. In today's lecture, we also discussed about few special cases if the constraints are of a different nature, or if we are trying to solve a minimization problem instead of a maximization problem, or in case if our problem is unbound, or if our problem has no feasible solution, or our problem has many or multiple optimal solutions. So in all those cases, how the solution is going to change, or particularly the simplex method is going to behave, we discuss that in today's class. With this understanding, I believe you will be much more comfortable using the simplex method for different types of linear programming problem. Now, one thing you have noticed, the number of rows in your tableau increases with the number of constraints. In many real-life engineering problems, you may end up with many variables and many constraints. If you have sufficiently large number of constraints, the number of rows in your tableau is going to increase, and as it increases, your computational effort is also going to increase. There is one distinct property of the linear programming problem which can be used to convert the linear programming problem possibly into a smaller size linear programming problem and then solve using the simplex method. When we convert, the solution remains same, however the number of constraints is going to change. We'll discuss about that, the duality theory of the linear programming problem, in the next class. Till then, thank you and see you in the next class.